Welcome back for some more reinforced concrete design. Now that we're nearing the end, let's look at detailing. And in particular, let's discuss some rules for detailing of reinforced concrete. Detailing should be consistent with the design models adopted for reinforced concrete members and should assure that the requirements for safety, serviceability, and durability are satisfied. Detailing requirements include minimum areas of reinforcement specified to prevent brittle failure, wide cracks, and to resist forces arising from restrained actions. Eurocodes limit the area of reinforcement in beams in a certain range that's defined by the minimum and maximum values. The minimum area of reinforcement is calculated as a fraction of the cross-sectional area of the beam, depending on the tensile strength of concrete and the yielding strength of steel. This table provides values of minimum reinforcement ratios depending on the concrete class. The area of reinforcement provided in the beam should be smaller than 4% of its cross-sectional area. In monolithic construction, where simple support has been assumed in structural analysis, partial fixity of at least 25% of the span moment should be allowed for in the design. In hogging zones of flanged beams, tension reinforcement can be distributed over the effective width of the flange. Part of the bars can be concentrated above the web. Compression reinforcement in beams should be held by transverse reinforcement with a spacing of at least 15 bar diameters. Shear reinforcement can be vertical or inclined, where the inclination angle of the latter should be at least 45 degrees to the longitudinal reinforcement. Shear reinforcement can consist of links enclosing the longitudinal tension reinforcement and the concrete compression zone, bent-up bars, cages, and ladders. Cages and ladders are cast in without enclosing longitudinal reinforcement, but should be properly anchored in the compression and tension zones. At least 50% of shear reinforcement should be in the form of links. The shear reinforcement ratio is calculated based on the beam width and spacing of the links and cannot be smaller than the minimum value, which depends on the strength of concrete and reinforcing steel. In designing the extent and number of links, the spacing requirements should be considered. Spacing of vertical links in both longitudinal and transverse directions should be smaller than 0.75d. The minimum and maximum values of reinforcement areas in slabs are similar to the ones adopted for beams. The minimum area of reinforcement in slabs is calculated as a fraction of the cross-sectional area of the 1 metre wide strip of the slab, depending on the tensile strength of concrete and the yielding strength of steel. The area of secondary reinforcement in one-way slabs should be at least 20% of the area of the main reinforcement, but not smaller than the minimum reinforcement area. To eliminate large unreinforced zones, the maximum spacing of bars in slabs is defined for the main reinforcement as a smaller value between 3 slab depths, or 400 millimeters, and for the secondary reinforcement as a smaller value of between 3.5 slab depths, or 450 millimeters. Note that the main reinforcement is placed in the working direction of the one-way slab, while the secondary reinforcement is placed in the perpendicular direction. For the areas of concentrated loads, these limits are reduced to a smaller value of between 2 slab depths, or 250 millimeters for the main reinforcement, and to a smaller value of between 3 slab depths, or 400 millimeters for the secondary reinforcement. The arrangement of longitudinal reinforcement in slabs near supports should adhere to the following rules. 50% of span reinforcement should continue to a simple support. For supports with partial fixity that is not taken into account in analysis, the top reinforcement at the internal support should be capable of resisting at least 25% of the maximum span moment, and at an end support at least 15%. In addition, the top reinforcement should extend to the support by at least 20% of the span length. Unsupported edges of slabs should be reinforced by U-bars with a length of at least 2 slab depths. These U-bars should be anchored by the top and bottom transverse bars. Shear reinforcement is usually provided for slabs thicker than 200 millimeters. Where the applied design shear force VED is smaller than the third of the crushing resistance of the inclined concrete strut VRD max, shear reinforcement may consist entirely of bent-up bars or of shear reinforcement assemblies. The maximum longitudinal spacing for vertical links is 0.75 d, and for bent-up bars it is d. The maximum transverse spacing is 1.5 d. Sufficient reinforcement should be provided at all sections to resist the envelope of the tensile force. This should include the effects of inclined cracks in webs and flanges. Curtailment of tension reinforcement is based on the envelope of tension force derived by adding the additional tensile force delta FTD obtained from the shear design to the tensile force developed in the reinforcement due to bending, where the latter is obtained by dividing the maximum bending moment in the section by the lever arm. The offset of the tensile force envelope should be performed using the additional tensile force delta FTD or the distance AL, where AL equals half of the lever arm Z times the cotangent of the strut inclination angle θ minus the tangent of the angle between the shear and longitudinal reinforcement. For members without shear reinforcement, delta FTD may be estimated by shifting the moment curve by a distance A1 equaling the effective depth of the section D. Longitudinal bars should extend beyond LBD plus AL. In addition, at least 1/4 of the bottom steel should be extended to supports. To understand the effect of the additional tensile force and curtailment requirements for reinforcement, we consider a diagram showing the envelope of the tension force in the longitudinal reinforcement. This is the curve showing the envelope of tension forces developed due to hogging bending moment in the end span. This curve is offset by the additional tensile force. This offset is obtained by moving the points of the curve vertically by delta FTD. Alternatively, this offset can be obtained by moving the points of the curve horizontally by the distance A1. To be able to resist the tension forces, the steel bars of the longitudinal reinforcement should be extended by the anchorage length, LBD, beyond the envelope of tension forces. Due to limited number of bars, the envelope of forces in the longitudinal reinforcement has several steps. The same rules apply in hogging areas above internal supports. This slide depicts simplified curtailment rules for top bars above middle and end supports, and for bottom bars in internal and end spans. As you can see, reinforcing bars extend a certain anchorage length beyond the bending moment envelope. Bending moments vary along the beams. This means that less reinforcement is required away from critical sections. Curtailment of longitudinal bars in beams is a way of reducing the area of tensile reinforcement at sections where bending moment is minimum or zero for the purpose of achieving an economic design. Here you can see the curtailment requirements adopted in the UK for longitudinal reinforcement in simply supported and continuous beams. In simply supported beams, 50% of the bottom reinforcement required in the span should be extended to supports. This amount is reduced to 30% in continuous beams. Away from the support, the top reinforcement in continuous beams can be reduced to 60% and then to 20% of the required amount above the support. The arrangement of reinforcement in a slab depends on the number of spans. Eurocode 2 requires only 50% of span bottom reinforcement to continue to supports, and 50% of top reinforcement above the supports should extend into the span. Here you can see the curtailment rules outlined for a simply supported slab and for a continuous slab. Bottom reinforcement should be anchored into the support. For end supports with little or no fixity, bottom reinforcement should be designed to resist a tensile force of 0.5 VED to allow for tension induced by shear, and the minimum bottom steel should be equal to 25% of that provided in the span. For end supports with fixity but analysed as simply supported, top reinforcement should be designed and anchored to resist at least 25% of the maximum span moment. The tensile force that should be resisted by the bar anchorage length is calculated depending on the applied tensile force induced by shear and an axial force in the member. The anchorage length, LBD, is measured from the line of contact between the beam and support, as shown on this slide. The design anchorage length is calculated using the equation 8.4 in Eurocode 2. As you can see, it depends on the basic anchorage length, LBRQD, and the effects of the form of bars, concrete minimum cover, confinement by transverse reinforcement, presence of welded transverse bars, and the pressure transverse to the anchored bar. The parameters influencing the design anchorage length are defined in Table 8.2, depending on whether the analysed bar is in tension or compression, and on the location of the bar in the cross-section. Where supports are too small to allow for straight anchoring of reinforcing bars, alternative anchorage methods can be applied. These methods are defined in Figure 8.1 of Eurocode 2. As you can see, the anchorage can be bent by between 90 to 150 degrees to the original direction of the reinforcing bar, creating a hook. Additionally, the anchorage can be looped or enhanced by welding transverse bars. The design anchorage length also depends on the minimum concrete cover, which depends on the position of the bar in the cross-section, defined in Figure 8.3. For corner bars, the minimum cover is the smallest between the bottom and side covers. The basic anchorage length is calculated using equation 8.3 in Eurocode 2, depending on the diameter of the bar, the ultimate bond strength FBD, and the design stress of the bar at the position from where the anchorage is measured from. The minimum anchorage length of the tension bars is the maximum value between 30% of the basic anchorage length, 10 bar diameters, and 100 millimeters. The minimum anchorage length of the compression bars is the maximum value between 60% of the basic anchorage length, 10 bar diameters, and 100 millimeters. The ultimate bond strength is calculated using equation 8.2 in Eurocode 2, depending on the design value of concrete tensile strength, the quality of the bond condition, and the position of the bar during concreting and the bar diameter. The quality of the bond condition is defined in Figure 8.2. As you can see, bent-up bars and bars in concrete members with a depth of less than 250 millimeters are considered to have good bond conditions. For concrete members deeper than 250 millimeters, only the bottom bars are considered as having good bond conditions. The values of the ultimate bond strength and the basic anchorage length are given in this slide for different concrete grades and quality of bond conditions. As you can see, the ultimate bond strength increases while the basic anchorage length decreases with increasing concrete grade. Note that the values of the basic anchorage length are calculated based on the full stress and have to be multiplied by the ratio of required to provided anchored reinforcement. At internal supports, the bottom reinforcement should be extended by at least 10 bar diameters beyond the face of the support. Hooks and bends can be used to anchor bars of at least 16 millimeters in diameter. Splice bars should be provided across the support with full anchorage lap on either side to achieve continuity and resistance to such factors as accidental damage or seismic forces. When the continuity of reinforcement between span is not assured, failure can occur at supports, as shown in this photograph. Anchorage of links and shear reinforcement can be assured by means of bends and hooks or by welded transverse reinforcement, as shown in the slide. A bar should be provided inside a hook or bend. The length of reinforcing bars is limited by shipping and handling constraints. Therefore, laps are used to transmit forces from one bar to another within concrete members. Lapping of bars can be done with or without bends and hooks, welding, and using mechanical devices. It is important that laps do not cause cracking and spalling of concrete. Laps are not normally located near high moment or force zones. Mechanical couplers can transfer load in tension compression or in compression only. There are several types of mechanical couplers, 7 types of which are listed here. As you can see, bar coupling techniques are based on using bar end threads, threaded studs, hydraulic swagging, wedging, and lock shear bolts. The clear distance between lapped bars should be less than 4 bar diameters or 15 millimeters, otherwise the lap length should be increased. The longitudinal distance between 2 adjacent laps should be at least 0.3 of the lap length L0. The clear distance between adjacent bars should be at least 2 bar diameters or 20 millimeters. The lap length is calculated using equation 8.10 in Eurocode 2. This equation is similar to the equation 8.4 for the calculation of design anchorage length discussed earlier. The only differences are that equation 8.10 disregards the influence of welded transverse bars and considers the percentage of reinforced lapped within 0.65 L0 from the centre of the lap length using the parameter alpha 6. The minimum lap length is evaluated as the maximum value between 0.3 times alpha 6 times the basic anchorage length, 15 bar diameters, and 200 millimeters. Transverse reinforcement is required in the lap zone to resist transverse tension forces. Where the diameter of the lapped bars is less than 20 millimeters, or the percentage of lapped bars in any section is less than 25%, then any transverse reinforcement or links necessary for other reasons may be assumed sufficient for the transverse tensile forces without further justification. Where the diameter of the lapped bars is greater than or equal to 20 millimeters, the transverse reinforcement should have a total area of not less than the area of one lapped bar. The transverse bar should be placed perpendicular to the direction of the lapped reinforcement and between that and the surface of the concrete. I hope you enjoyed hearing about these rules for detailing of reinforced concrete. Join me again next time where we discuss some more detailing.